Okay, thanks for coming along, guys, to this last session. It's only the bravest and strongest that are still hanging in there. Okay, so I'm going to talk to you about multi-scale integrated interpretation. And I'm going to use a project in northern Chile and a porphyry exploration play called Victoria as our example project. And really what I want to do is talk about all these tools that we've talked about throughout this conference, and many of them have been presented in quite a lot of detail, and how we might turn them into an exploration decision-making workflow in a mineral systems context. So it's all very well to have these tools, but how do we then integrate them into a process to make decisions to go forward as a business? So really it's about going from northern Chile, and you can go anywhere you like, to placing, find my pointer, placing 2 drill holes on a pampa plain to discover a previously unknown porphyry system in a world-class terrain. As you can see, these sort of images are more and more common to us now, especially in mature districts where there's not a whole bunch of outcrop. We're working largely blind and we have to leverage the data all the data we've got. The names on here are those, myself and those that I've stolen images from and worked from directly, but really I'd like to cite the entire South American exploration team in working on this program because it was a very collaborative effort. I come from a geophysical background, and I leverage the experience and expertise of other people in the group to supplement my own knowledge, and I think that's a really key part of any integration, is using the right people at the right time to help you. There we go, lovely. Okay, so one quick slide on mineral systems. I think Cam McQuaig's presentation on day 1 was really good, and we think a lot about mineral systems, and First Quantum buys into them, and there's a lot of ways we can talk about them, but really I like to set them in the scene of, it's a conceptual model of processes and their relationships is a really key part of this, how they relate in time and space, that may result in ore formation. So it's really all about that predictive scale, and really what they're saying, I believe, is that if you have all these ingredients, you might get ore. It doesn't guarantee ore, but if you're missing one of these critical ingredients, it guarantees you no ore deposit. And that's pretty helpful. That's a where not to explore filter. But we also have to set it in operating reality as an exploration business, in that we're under a lot of pressure from boards. They're demanding, they need to know where to put their money, and we need to give them a reason to direct their money into our exploration plays rather than brownfields or other sort of studies. And we're very resource limited. At the end of the day, there's not many of us that have to go around. There's never enough money, there's never enough time. And we've got what I call the rise of the machines, which is really a lot about what we've seen today, this incredible wealth of data that we can now collect relatively cheaply, but in many cases needs specialists to understand it. And none of those new data sets are silver bullets. None of them show you where the ore deposit is in and of themselves. They simply augment and assist the explorationists and traditional techniques and make us better and more efficient, but only when we use them correctly. Okay, a quick plug for First Quantum, but really I think our response to that is all around being flexible, multidisciplinary teams. So in our group, we move across regions a lot, we move across commodities a lot. I've just gone from porphyries to sediment-hosted copper, to share our ideas and our understanding. We obviously also need sound scientific grounding, embedded consultants. We don't consult people in and out really quickly. We prefer to have them as a key part of our team and really work with us quite closely and help us solve our problems. Be open-minded, because you can guarantee things won't work out as you expect them to at the start. And be risk-aware, but not risk-adverse, and I mean that from a technical side. A no-blame culture is important. What we do is challenging and difficult, and if we consider failure and mistakes as a massive negative, we're missing the opportunity to learn. We don't aim to make mistakes, we don't aim to fail, but we need to make sure we learn from those and not blame and not seek to avoid taking risk, because then you just won't find. And adopt technology. We want to be on the forefront of the technologies and make sure that we're early movers in that space. So for all of that, and for all the rise in machines and the data, I truly believe that nothing at all happens without people. Data won't tell you where ore deposits are. They're born in the brain, and the data you have to filter through that data to find them. And this project in particular had a wealth of contributors throughout the process. And I think we did quite well at getting the right people involved at the right times with our limited resources to push this project along. And it probably took 2.5 years of intense exploration really to move this through the exploration pipeline. So I'm not going to talk much about northern Chile because I don't have that much time, but as we all know, it's a world-class porphyry location. And it's quite mature, which is great because in some respects, because it gives us good to moderate regional data sets we can work with in the early predictive stages. There's a lot of discoveries, but not many that have been made under cover, and there's quite a lot of cover in northern Chile. So it begs the question, where are the deposits under that cover? So the project that I'm going to talk to you about today is located in here, and this is the Greater Victoria District, a large consolidated tenement package First Quantum was able to control through various joint ventures, located more or less equidistant between La Escondida and El Salvador in the gap. And if you buy into fractals, that's where the deposit should be, because if you step up, you go into Chuquicamata and those sort of systems. But how did we get there? Note, it's also not an area with any giant significant ore deposits, so quite anomalous in the Chilean context along the Domeyko Fault Corridor. So regional area selection, this is the really predictive stuff. This is the real mineral systems concepts. And I'm showing you here a prospectivity map generated by Alex Farrar. There's various iterations of these, and they're always a work in progress. But the key to them really is that they're driven by a small number of fundamental criteria. So where is your porphyry window? Where is your fertility? Where are your batholiths? No batholith, no porphyry. How can we map those? What are the structural domains and when are they favourable? Now, to do all that, to input those interpretive ideas, you need data. But you need to convert those data into ideas before attempting prospectivity mapping, because then you can test your idea and see if it works and change it. It's dynamic. And it's all about where could we have a porphyry at this stage and where can't we have one. So, these things are rapid and they use freely available data for the most part. And they need to be temporal. So this example actually is for the Eocene, Oligocene. And for a traditional sort of arc position, if you're going for a back arc system, a taka-taka type thing, you'd need a different set of criteria and a different set of ideas to go look for that. So in this example, you see the El Salvador cluster and Escondida light up very nicely. And then in the gap there, where Victoria now sits, and that scale bar is 50 kilometres, was the position that we controlled. And you see there's quite a large number of prospective or fertile areas based on the inputs we used for this particular data set. Resist the temptation to include superficial data, because it will bias you in covered terrains back to what you already know, and you'll find the old ore deposits. So this does not include copper occurrences and the like in these data sets. Okay, so now we're into Victoria and we need to get moving. I'm going to now focus on just the northern part, Victoria Norte, which hosts the Pampa Vaquia system, which sits down here. So what I'm trying to show here on this image is the outcrop distribution in grey, and you'll see that in the mineral occurrences, small scale, that occur around the project. Where you have outcrop, you have mineral occurrences. That's a good sign, despite the limited amount of outcrop available to us here. And we have occurrences of different styles, dacite porphyries, epithermal veins. This is a Cretaceous copper moly porphyry over here. And the green dots are all the drill holes. A bit like David Wood's presentation this morning, there's a lot of drilling in the Pampa in Chile, and you can leverage that data if you think about it smartly. The other side of this is actually a geophysical image of gradient IP, but alongside that, with all this historical data, there was over 20 years, mostly by majors, to be honest, but with different tenement packages. There's 14 magnetic surveys, over 100 drill holes, most of them short. There was, I don't know, perhaps 4 or 5 different IP surveys collected here, all different, none of them ever collated. So there was a huge collation program at the start of this project, which took several months to get this data into one space, to one environment, and standardized. And 3D inversion of the geophysical data sets here was particularly important once they were brought together, given the absence of our exposure. So project scale context was huge here, and this was the real data-heavy data mining stage for us to get through. And I'll just point out this large IP anomaly here in the gradient IP, which looks very well tested, because that'll become more important later. So now we've got our data in some order, let's get out into the field. There isn't much exposure, but you have to understand the exposure that you've got. And these are some images from Simon Jones doing some structural mapping in the limited exposure we have in the quebradas. to demonstrate that, yes, okay, the faults are all mapped as thrusts, and yes, they are thrusts. But that thrust movement is quite modest, and these faults in this region are all essentially dominantly extensional. And so that's quite in contrast to what you would see in the CERN GeoHim, the surveys mapping and so forth. And it was extracted from relatively limited outcrop and a lot of footwork. We also got around the drill spoils, a bit like what the QPX example this morning, finding and confirming pyrite-sericite alteration of a porphyry affinity linked to that, remembering our big IP anomaly, so quite exciting. So then we thought, let's date the sericite. We've got Cretaceous mineralisation in the area, and the dating actually confirmed a 39 plus or minus 1.4 age. So we're in a favourable Eocene window with two giant Eocene deposits on either side of us. So now it's getting kind of interesting. We're getting kind of excited. And, you know, we talk a little bit about green rocks and what the propylitic can tell us. Well, we've got sphalerite in our propylitic here, quite distal, so we know we're fluxing metal. We've got some of the right fluids around. And there you go, just understand the Strat. So this was, again, produced by Simon Jones, who did a mapping program out here. Once you understand your Strat and where, oh, pardon me, what have I done? Go back one if I can. Yep. Once you understand your Strat, you can actually think about the geophysical response of that stratigraphy and what's anomalous and what's not anomalous in that package. We still had some questions though, some fairly serious ones. How deep is the cover? Cover depth being a major issue and, you know, a serious economic impediment to fairly low-grade, large tonnage porphyry systems. So our solution to that was actually to do something a bit different, and it's not the first time we've done it at First Quantum with some success, but to do some regional gravity acquisition across the pampas. And then to take that gravity data and constrain it through explicitly constrained inversion, through GoCAD VPMG, working closely with Mirror Geoscience and the irredoubtable Glenn Pears, who shares the stage with me here now. And that's a really powerful technique because you can domain it by geology and geophysics. You can really think about it, you can limit the density variations, and you can use the drill hole pierce points you have. We didn't always have all the assays, but we often had pierce points depths to map that basement in quite a lot of detail and produce 3D surfaces and the like. So I show it here in 2D. This is the depth image here, but obviously this can be integrated in a 3D environment, and you can see the cover varying from virtually outcrop or outcrop where it is in deep blues, up to about 300 metres out in these northern domains. So just a reminder, the IP anomaly at Pampa Vaquillas actually sat down in this relatively shallow domain here, and this is a small epithermal system. So we were able to quite quickly reject some quite large areas as probably not prospective for an economically mineralised system and target the shallow areas. And that impacts the way we drill test this thing and how much money we can put towards drilling and where we put it. So understanding the data in 3D. Leapfrog is a great tool that we use a lot now to understand our data in 3D. I'm going to have to keep moving pretty quickly. But basically, this is an image taken of around the Vaquillas system. And what we've done here is actually the 3D interpretation of the IP data, which remember was piecemeal. It had never been, most of it was 2D lines. We also had gradient. We've put it together, 3D inverted it. You can see the Picaron copper moly system out here with some drill holes in it. And over here, we see the very large Vaquillas IP anomaly, which we all presumed had plenty of drill holes in it. But when viewed in 3D, we could see that actually no, it had been very weakly or poorly tested, only marginal to the system, and had really not attracted as much attention as one might expect it to. So we're starting to get an exciting target here. It's got a scale. This is about 5 kilometres long. So certainly on the right size scale. But we hadn't really seen any plumbing to the system, and we hadn't seen many intrusive rocks. Thinking mineral systems were sort of missing a key component. How might we be able to image it? We don't have much cash. It's in a bit of a downturn. But we managed to do some fairly low-cost MT sections across the project, trying to locate them intelligently. They more or less were 1 to 1.5 K spaced, and targeting various different parts of the system as we saw it. This is a magnetic image underneath with the IP contours and the drilling. So you can see constantly every image you'll see here is more than one data set playing at once. Once we did that MT, and it was deep looking MT, we didn't do IP, we already had the data. What we saw was pretty fascinating. We see the IP anomaly is quite well fault bound, and we crossed that fault with these MT lines. What we saw was on the western side of that fault line, there was this large, very low resistance zone down to sort of 15 ohm meters. We can't really explain it. It's about 4 to 5 kilometers down. And from that, you see the series of subvertical resistivity lows that seem to be sort of utilizing that, what we were calling the western boundary fault, which is mapped on here, as access up to nearer the surface. And when then you took that a little further, and you look at where those subvertical features are with respect to the chargeability anomalies, you see that they're spatially consistent with each other. So, wow, well now maybe we've had a look under the hood of this system and it could be pretty good. That's really interesting. So we integrate that, all that data together as a drill proposal. And our drill proposal was about understanding the system still. We were hopeful we knew where the best place to drill was, but our system was still 5 kilometres long. We had bits we preferred, strong high-ranking bits and lower-ranking bits, and we needed to preserve cache. So we still tested the whole area, but we used RC drilling where we felt there was lower probability and diamond in the high probability areas. Note, this little area here is actually a mag anomaly that will become important later that we avoided because there was post-mineral magnetic diorites elsewhere. These are all the alteration assemblages as interpreted prior to drilling. And for every drill hole, once you've got this sort of plan view concept, you've then got a section concept of what success looks like for that drill hole. So this is one of our highest priority drill holes at the time, and that is built conceptually. It's essentially an imaginarium, but it's based on real data and it's a real idea. And as you drill that hole and as you track down that hole, you can decide whether or not this idea is holding up or how it needs to change and then move your drilling accordingly. I think things like this are effectively mandatory for all drilling programs. They'll nearly always be wrong, but you've got to have an idea to know that it's wrong. So results in our first phase were exciting. We got lots of porphyry-style veins and alteration, lots and lots of pyrites, so we've explained our IP anomaly. But we didn't get any copper and we got no intrusive units. That's not great. We did, interestingly, intersect quite a bit of gold. And in fact, in one hole, 362 metres at 0.4. So a reasonable amount of gold, and you probably can't see this very well from back there. Tiny amounts. In the same drill hole, we got our best copper, which is effectively 0, but still zoned. The moly, which is actually quite nicely zoned with respect to the copper and gold, and zinc. So the system's actually behaving reasonably normally. It's just that we haven't found gold and we haven't found any early mineral intrusives at all. So we were a little bit puzzled because we're getting this gold associated with magnetite in an area where we didn't really anticipate it. We were looking for copper moly systems at this time. We then went big on the techniques that a lot of people have been talking about in quite a bit of detail with this drilling. We took ASD, we did petrology, detailed relogging with porphyry experts that have worked in Chile for a long time. We did fluid inclusions. Could this fluid carry copper around? Is there any fundamental reason why it can't? And everything said, no, this system's still alive. Maybe we haven't found the best bit yet. Until we've drilled the porphyry, we don't know. So here was our interpretation of the data at the time, and you definitely can't see the little tiny heat vectors on this. I'm sorry, it's from the paper. But effectively, there was an amazing coherence and consistency with the data, all pointing back to the gold-rich anomalous zone as sort of where we need to think about. And likewise, when we looked at prograde alteration assemblages, it all vectored back into here. And of course, invariably, the one hole we lost in drilling, that stopped shallowly here. So there's a lot of peer review, observation, interpretation. So that's what this is all really about. So we went back to the data, thought about it. It became increasingly clear that our porphyry vein density was really kicking up all through here. And when you compare that to where our mag anomaly is, the magnetic anomaly suddenly becomes particularly important, an area which we actively avoided in the first phase. Then go back and do some modelling, constrained with depth, but not with mag sus. But what you're seeing here is mag sus down the hole and the mag inversions. And you see that, yep, a near miss scenario looks likely. This is actually flipped. So this is actually the fault zone in here and the shallower body in there. So we don't really understand the system as well as we'd like to. We're in a world-class address, so we decide we're going to persist here. This is a hold or fold scenario. Our system, we've explained the big IP anomaly really as a phreatomagmatic breccia full of pyrite, but we don't know what's going on down in here. We don't understand it well, and we've got to remember where we are on the planet. So we decide we're at last chance saloon, but we can drill to answer here with a couple of drill holes. So that's what we did. We decided to collar in and drill that mag anomaly top dead center. And the results of that was that we found the causative porphyries, multiple porphyries, dioritic, early gold associated with magnetite, quartz pyrite veinlets, mineralisation from just 70 metres. So just to say it was, with our gravity modelling, it was very accurate where the andesites were. Post-mineral barren phases, and significant post-mineral movement when we drilled on the other side of the western boundary fault, something we hadn't predicted. So a fascinating result, really, because what we really seem to see here is banded quartz veins, and with the alteration assemblage is really just a gold-rich dioritic porphyry system where it shouldn't be, as far as we understand these things. So a fascinating result. Now we understand, now we think we understand at least, what's going on at Pampa Vaqueus. And I'll move very quickly because I can see I've run out of 20 minutes. That, you know, we've got an early mineral porphyry that's come in with some gold and moly, scarnified some sediments at depth, and we believe linked to the Vaqueus system over here. We've had some later mineral phreatomagmatic event that's brought in this huge pyrite sericite overprint, which is what we see in the IP anomaly, and not directly linked to mineralization. It's essentially barren. And then we've obviously buried this, left a shoulder of the epithermal breccias out here, dumped some gravels on the highly erosive phreatomagmatic breccias, which are clay-rich. And then obviously we've had some serious post-mineral movement, which has cut the system off to the west and limited its size potential quite significantly. So you get to sort of another hold or fold question. You're still there. You still have to decide whether you're walking away or not. And there's a few choices. You could say, well, is there an entirely different system? Can we date the intrusive and find out that, hang on a second, it's not actually 39 MA like the sericite, it's more like the Cretaceous Picaron porphyry. We've still got this deep MT anomaly that no one's been quite brave enough to put an MT drill hole in, albeit it's spatially consistent with the position of the phreatomagmatic breccia. So we felt that, no, the data sets we had were not encouraging, implying a second system, at least not one at explorable depths. You can chase the gold. How good is Pampa Vaqueus? That's not a target for us. That's not what we're about. So we decided to fold here. We did try petrophysics, by the way, but unfortunately lost most of the holes downhole. So we were only lost most of the holes, sorry, and couldn't get the probes down. So we did do some handheld just to say, I'm a big believer in petrophysics. This hasn't been fed back into the system because we folded, but had we not, I think we would like to have used it. So just as some wrap-up comments, I think like the use of domain experts and the right tools at the right time is really critical here, and ensuring that you're integrating data with ideas. So all the way through this process, there was ideas. There was a porphyry model. We were trying not to drill a geophysical or a geochemical anomaly. It was about the model. We had a lot of management support to get this done and take it to an answer, and there was a lot of surprises along the way, and you've got to roll with those punches. Was it an exploration success? But what it definitely was is a huge learning process, and we're much better off and we're much closer to finding the next one because we went through that process. So that's it. Thank you.
Probably got time for one quick question while we set up for the next talk.
Cool.
I have a question, actually. No, not going to let you get away with that. No, I was just interested in the fact that you cycled back on a number of data sets throughout the process. And was there one data set that you found that was particularly useful, either as you know, in one single form or a derived form as well?
Actually, I'd probably say no, in the context that I think it was always about using multiple data sets. Okay. I think I sort of avoided sort of the idea of getting limited into one data set. So I think that's kind of the important part about it is very rarely one data set is the answer. There's always like how you use it with respect to the context of another data set. Yeah. Okay.
Excellent. Thank you.
Thank you.